A very good afternoon to my teammate. My name is WILFRED and JEFFRY. My matrix number F25A1809. Okay, today I will present about the interactive project. It is the broiler growth derivative simulator. So for the develop for SFH animal husbandry technology. This tool, this tool combines biology, science with mathematics, following Malaysian agriculture standard. Okay, for the first is look at the main issue we are addressing. Okay, for the in commercial poultry farming using the popular breeds like Scots 500 or Ross 308. For the broiler chicken do not grow at the standby speed. Instead, their growth follow what we can sigmoidal or S for shape curve. This mean grow starts slow and then speed up in the middle and slow down again towards the end. Okay, for the importance in Malaysian, okay, in Malaysian, feed make up almost 17% of all production costs. That's mean efficiency directly determine profit. Now, if you look at the green culture, the growth rate, you will notice it rise, reach a highest point, then start to drop. Uh, from zero, and then highest, and then drop again until 60 daily gain velocity for gram per day. And then that higher point is called the peak derivative. This is the most critical stage. Okay. Before this point, every kilogram of feed gives you more weight gain. After this point, growth slow down, feed conversion become less efficient, and you spend more money just to get smaller result. Okay, for the explanation, Wmax is maximum weight. That's the heaviest weight the chicken can reach. And then changing this move the top limit to the grow curve. And then for the growth rate, control how fast they grow. Higher value sama dengan how to say it, and then faster growth reach peak early. And then for the environment factor, adjust result based on farm condition like temperature and ventilation. Sustainable for local Malaysia, closed house for the system. And then for the recommendation for improvement, finally, I would like to share one key idea to make this simulator even better and more useful. And then correctly, user have to move the slider manually to find where the green curve is highest to make it easier. We can add an automatic optimal harvest calculator. Okay, that is all from me. Thank you.
Good morning, everyone. My name is Yong and my matrix number is F25A1629. Today, I will present my project titled Optimizing Malaysia's Oil Plants Use Using Derivatives. This project combines bioscience, mathematics, and technology to study how oil plant use change over time and how derivatives can help improve plantation management. The bioscience problem chosen in this project is the growth patterns of Malaysian oil palm fresh foods branch FFB yields. Oil palm yields does not increase at a constant rate. Instead, it follows an S-sharp growth curve. During the early years, the growth is slow because the plants are still immature. As the trees mature, the yield increases rapidly before eventually becoming stable in older years. Because of this changing pattern, plantation managers need to know when the plants grow the faster, when fertilizer should be applied, and when production begins to slow down. To analyze this, we use derivative from calculus. Studying this bioscience problem is important because oil palm is one of the Malaysia's major agricultural industries. By understanding yield growth, farmers can improve fertilizer management, increase productivity, and reduce resource waste. This project also shows how mathematics can be applied in real-life agriculture technology. This HTML website contains an interactive graph with two important lines. The green line is represent the cumulative yield function, which shows the total oil palm yield over growth rate. The orange dashed line represents the derivative function, which shows the growth rate of the yield. By comparing these two lines, user can clearly understand the relationship between total production and production speed. When user click one, when user click on a point in the graph, the system explains the meaning of that year. For example, below 4 years old, the derivative value is low, meaning that the plants are still young and growing slowly. Between 4 and 7 years, 4 and 7 years, the derivative become much higher, showing that the plantation is entering a rapid growth phase and requires more fertilizer support. After 10 years, the derivative approaches zero, meaning that the yields become stable. This interactive analysis helps users understand the meaning of each point on the graph more easily. One of the recommendations to improve this HTML website is to add over tool tips and animation effects. This will make the website more interactive, easier to understand, and more professional for use. So, in conclusion, this project successfully demonstrates how derivative can be applied in bioscience and agricultural technology. That's all for me. Thank you.
Assalamualaikum and good day. My name is Muhammad FIRAS bin Muhammad SIDEK and I am an undergraduate student majoring in SFA Agrotech. Today I am excited to demonstrate how we can bridge the gap between complex mathematical calculus and practical Malaysian agriculture. I have developed a specialized web application using HTML and charts to visualize the optimization of smart fertigation system, specifically focusing on the our local chili coli production. In a smart farming, we manage plant nutrition through electrical conductivity (EC). The bioscience problem we face is finding the Goldilocks zone for nutrient concentration. Plants do not react to fertilizer in straight line. They follow the quadratic curve of growth. If we provide too little EC, the plant is stunned. However, if we exceed the biological limit, we encounter nutrient toxicity. In Malaysian tropical climate, managing this balance is difficult because high evaporation rate can quickly concentrate salt in the soil, leading to quickly the root dehydration. My application models is relationship using the function fx, where is x is the EC level and fx is the resulting plant biomass. Why is studying this so critical? First, economic efficiency. Fertilizer is the highest variable cost in fertigation. Over applying is waste of money. Second, biological sustainability. Excessive nutrient lead to soil salinization and environmental runoff. By using the first derivative, fx, we can calculate the marginal growth rate. This tells us exactly how the mass biomass we gain for every additional unit of fertilizer. In essence, calculus allows us to move from guessing our fertilizer rate to calculating them for maximum ROI and plant health. Okay, let's look at the live model. At the point 1.0, as we can see, all right, as we can see, the derivative effects is high and positive. In layman terms, the plant is hungry. Every gram of nutrient at here resulting is massive jump in growth. This is efficiency zone. For the 2.0, if we look at 2.0, the optimal peak. Look at the calculation. Fs is now is 0. In calculus, this is the stationary point. Biologically, this is the peak productivity. Adding more fertilizer beyond this point will not result in any more growth. We have reacted the plant biological maximum. And look at the 4.0 at the graph. Now the derivative is negative. This is a warning. The negative rate of change indicate the adding negative rate change indicate that adding more nutrient is actually decreasing biomass. This is represent osmotic stress, where the high salt concentration in the medium is actually sucking water out of the root, leading the plant death. Okay, to make this HTML application even better than more industry ready, I recommend integrating a real-time IoT API. Currently, the data is modeled based on fixed MARDI standards. By connecting these web apps to a live node RAID or Firebase server, link the actual ECA sensor in the greenhouse, the graph could update automatically based on a live environmental data. This would transport the application from static educational tool into a live decision support system that could automatically triggered irrigation pump when the derivative indicates the plant has reacted the optimal zone. So, in conclusion, calculus is not just a classroom exercise. It is the language of plant growth. Thank you for your time.
Hello, good morning, good evening, and good afternoon to everyone. My name is Nur Ifa binti Ahmad Shukri, and my matrix number is F25A1419. And I am a student majoring in Animal Husbandry program. Today, I want to present my interactive web application. It combines software development with biology to show how we can use basic math tool called derivatives to manage a real-world aquaculture farm here in Malaysia. For this project, I am focusing on the growth model of the black tiger shrimp. So let's look at the bioscience problem. In shrimp farming, animal feed is the biggest challenge because it is very expensive. In fact, feed takes up to 60% of a farm's total budget in Malaysia. The problem is that shrimp do not grow at the same speed every day. When they are babies, they grow slowly. In the middle of their life, they grow very fast. But when they become old, their growth slows down again. As farm managers, we face a big dilemma. If we harvest too early, the shrimp are too small. But if we harvest too late, they grow very slowly but still eat a lot of expensive food. This wastes a lot of money. So next we are going to questions. Why is it important for us to study this problem? First, it is about economic survival. With high feed costs, Malaysian farmers cannot afford to guess anymore. Studying this problem helps us find the exact day when feed conversion is at its highest efficiency. Second, it helps us plan our harvest logistics. By knowing the exact growth speed, we can predict the best week to empty the ponds, pack the shrimp, and send them to the local markets at peak quality. In short, studying this helps farmers save money and maximize profit. Now, let me show you how this interactive app works. The green line is the total weight, and the orange dashed line is the derivative, which tell us the speed of growth per day. Let's click on three different points on the timeline. First, I click on day 30. The app shows the juvenile leg phase. Here, the growth speed is very low, only 0.1 grams per day. This means the baby shrimp are using food energy to build their baseline organs and immune system, not for gaining weight yet. So farmers should focus on high protein starter feeds here. Second, I click on day 65, 63, 65, 66. So this is the inflection point or peak day. Look at the derivative. It hits the maximum speed of 0.568 grams in single day. This means the shrimp are converting food into meat perfectly. The math tell us do not harvest now, let them enjoy this high growth boom, but keep the water oxygen levels high. Third, I click on day 100. Day 100. The shrimp are big now, around 31 grams, 30 grams, but the growth speed has dropped below 0.192 grams per day. Biologically, all shrimp spend most food energy just to stay alive, not to grow. Keeping them longer is a waste of money. So the derivative warns us that growth has slowed down. It is time to harvest right now. So to wrap up my presentation, I want to recommend one way to make this HTML application even better in the future. Right now, our model uses fixed numbers for growth. To improve it, we can add input boxes for daily water temperature and dissolve oxygen levels. Since shrimp growth change depending on the water condition, connecting the derivative formula to live water sensors will give farmers a much more accurate real-time prediction on their shrimps. That is all from me. Thank you very much.